Okay, well, it's a pleasure to introduce Professor Jeff Cook. He has a very long career. He's been like all over the world. He did his PhD in San Diego. Then he was at UC Irvine and went to Australia with a fellowship. That's the ERC one. That's rather famous there. That's actually when I met him at Swinburne University of Technology, where he's been since then. Full professor, and he's worked in many, many different things, from high redshift galaxies, transients, supernovae, and also developing a lot of the instrumentation that it's needed for in 10-meter telescopes to kind of like find these objects. So he's going to talk about proposition, or let's say like a possible instrument to be brought here at the GTC. So,
Zana, I appreciate that. Hello, everyone. Just so I get a sense, how many people are researchers and no instrumentation and instrumentation? Okay, just trying to gauge how much to cover. Okay. All right, so this slide you've been staring at for a while is just the opening slide for this imager. It's a wide field imager at degree across that is designed to take it or to fill the many, many gaps that are in imaging today. Even though we have things like Rubin and there's an 8-meter, the Subaru Hybris Prime Cam, there remain many things that they don't do that we need to progress science. And I guess everything you need to know right off the bat is just listed there, right? It's the most powerful wide field optical imager on Earth or space for the foreseeable future. And that's not hyperbole, that's true. So for the next several decades, we have what we have now. There's nothing planned, and I can explain why that's the case. This would be the only thing that could fill those gaps. As mentioned there, it does have these capabilities that can enable a number of science cases that cannot be done otherwise, and some new modes of science. Okay, so there's a bunch of logos here for people involved, and it's a partnership between different Australian universities and Caltech, UC California, and some industry partners. All right, so I'm going to first mention a little bit about the instrument really briefly, like what it is, so you have a sense of what the heck we're talking about. Then I'll talk about some motivation, why we would need this thing, some science, and then some more technical stuff about the instrumentation. That's basically how I've structured this. All right, that's the instrument team. Lots of people, lots of names. You're not going to know. Just know there are a lot of people. Okay, so there's like 80 plus people doing science, and there's about 40 so people doing instrumentation, which I'll talk about more later. Okay, so what is the wide field imager? Here's a nice little CAD drawing of it to the left there, and then a cutaway to the right with some of the main things labeled, just some parts. It's a very simple, straightforward, reliable, and powerful instrument. It's a big camera that's highly efficient, is the bottom line. It has high and very high ultraviolet sensitivity, which you'll see later, it matters a lot. And part of that is from the the smartly designed optics, which has just 4 elements, so very few surfaces, including all the way, so they just kind of have L1 through 4 here. Again, I'll cover this better later. But there's the blue are these lenses, there's filter kind of goes in there where the yellow is, and then the back there is the detector. And so that's it. I mean, the light only sees these. So imagine this being at prime focus, which I'll show you in a second. The light hits the mirror and then goes through these lenses only. So it's a very high throughput. These 4 corrector lenses means that it's light and inexpensive. And the fact that they're fused silicon means they're UV sensitive. It has a detector array. This is just one model of what it would look like. It's a degree across. It has CCDs, these large CCDs, so maximum area, minimum chip gaps. It also has CMOS detectors in the corner here, which I will talk about later. CMOS detectors image really quick. You can do sub-second sampling, so you can get really fast, high cadence imaging. And it's possible that the whole thing will be CMOS if CMOS detector technology gets sufficiently blue sensitive. But currently we're using CCDs. Oh, and that's just the field of view Osiris to give you an example of the size difference. Okay. Yeah. All right. So speaking of field of view, here's this field of view on the sky with the obligatory moon. You know, you got to compare it to something, right? And these are 2 imagers that can image in the optical and even into the UV with Hubble. But it takes about 45 pointings to up to 400 HST pointings to cover that field. So you can see how each pointing, you're doing a much more efficient science, firstly, if you want to cover a big area. And I'll show you later that it also goes into the UV, which OSIRIS doesn't. But there are also these infrared missions, space missions, both Euclid and Roman. That's their field of view there. So you can see with a single pointing, you can get their single pointing as well. And on a 10-meter telescope, it's okay, on a 10-meter telescope, the wide field imager can image head-to-head with Roman, for example. So Roman, however deep the depth it gets per second, you can get the same depth in the optical with this imager. So that becomes very powerful. So why would this be good for GTC? Maybe potentially in the future. And I can talk to you later about Australia and how, that can work out a partnership, et cetera. But it's because GTC is designed modular. So firstly, the 30-meter telescopes cannot do wide field imaging. They're not designed for that. 8-meter telescopes also have a very difficult time because you have to do a whole top-end restructuring. Either you have a top-end that replaces, comes on and off, or it's just difficult. But with GTC, the design, and you can see, I know people online won't see, but you can see this cage-like structure in the middle at the top there. That's the prime focus, right? That's where the instrument would go. You can see it here from the inside. It's up here in the upper right, that cage. So you'll see a picture of that cage later. Okay, that's the position it will be where currently is the secondary mirror. And if you take that telescope and you point it down towards the horizon, it comes to this platform here, which is like a horizon deck. Okay, so this comes down and you can actually access that easily, which is not the same for other telescopes. So it's built into the design of this telescope to have a wide field imager. It was initially designed to have that. This is that cage up close. And you can see there's a secondary mirror and some components behind that, but that rolls in and out. So you can just kind of roll that out. You can stick an instrument in and roll that out, et cetera. So that's designed to be modular. So it's a very beautiful design and very efficient for this type of thing. So here's this cage also. And one possible thing for this imager would be to have a deployable secondary mirror such that you could leave that imager in there and just have this secondary that moves up and down. So you can imagine that cage again is this cage. And then way off to the left is the primary mirror of the telescope. So the light comes in, hits the primary way off to the left, and then comes up to this secondary mirror, the yellow thing. And it would bounce back to the instruments currently. And that sounds great. But if you have it flip out of the way, you can, it's going to show here, flips out of the way, then the light can go straight to the camera. You could image, and then the mirror can come back down within a couple of minutes, and you can go back to some other instrument. And that capability is going to be fantastic because we are now in the era, I run programs that do this all the time, where we can take wide field imaging like that and process those data within a minute or two and actually find sources, look for transients or look for galaxies all within a couple of minutes. Where then you can flip that mirror back and then get spectra of that right after that, which is a fantastic capability, I think, especially for transients, but also just if you have one night on the telescope, you want to image and then get spectra of your sources. I think that's going to be a great capability. Okay, so now some sobering news. Okay, so right now we're kind of in this 10-meter world, I'll call it, where if you look over the last 20 years, here are a bunch of telescopes. It's not all of them, but it's some examples of them. And I've got like from 0 to 10-meter class size primaries on this bar. And you can see the different instruments, right? And you probably recognize many of those, right? There's 10-meter, 8-meter, 6.5-meter, 4, et cetera, all the way down the line. All the ones that are in bold have wide field imaging capability. And as you can see, as you get to the bigger telescopes, there's only these two, Rubin and Subaru, right? And here's where the landscape sits right now. GTC and Keck at the top there, doing great deep spectroscopy, et cetera, and leading the world. However, next year or so, plus 20 years, this is what the world's going to look like. All of those telescopes are now scrunched down there. If you rescale 40 meters to the 10-meter world, the ELT, which will be coming online soon, will be the equivalent of the 10-meter leader in the world, as you can think of it that way. So you rescaled it. Other big telescopes will be the 6.5 and 8-meter class. And everybody else is down there if in the same sense, right? If you scale it down. And so now GTC is sitting down over here kind of in a 2.5-meter class in a 10-meter world. And so when you think about that, this is going to happen within just maybe 4 years or so, 3 or 4 years. So if you're going to build instruments, you really have to think about what would you build on a 2.5 meter to keep it a liter, right? If you're building some instrument that's going for some special type of science, great. But if you're doing things that these bigger telescopes could be doing, you're going to be blown out of the water, right? And so having a thought about that, I first say that wide field imagers are just fundamental, period, to astronomy. They underpin about every type of astronomy, galaxies, solar system, transients, etc. They're everywhere. And you need images of what you're looking at. Okay, that's important. Also, all wavelengths, right? I mean, you have like radio, high energy, you find sources, you need an optical image. What is that host galaxy? What is that target? You need optical images. So there's this evolution that's occurred. A long time ago, 100 years ago, 1.2 meter telescopes were wide field imaging, actually using photography, okay, for 4.5 meter telescopes, and that worked really well. You get these wide field images, the 4 and 5 meter telescopes got spectroscopy, everybody was happy. Then came 10 meter, 8 and 10 meter class telescopes, and you have the 4 and 5 meter telescopes with wide field imagers. They're doing that task to find all those deep images, do those surveys for these larger telescopes. Well, now we're entering in the 25 to 40 meter world, and we need the 8 to 10 meter telescopes to do this job. It's just evolution, right? So also importantly, wide field imagers are the most productive imagers and highest demand imagers on their telescopes, their respective telescopes. For example, here is publications by telescope and different years there. Average is in this, or the total is in this pink line. And a whole bunch of telescopes are lined up there. You can find your favorite telescope along the way. But it has some radio telescopes listed here. And so if I get rid of those radio ones, these are the ones that are optical infrared. Okay, if you want to just look at these. So these are the telescopes and their number of publications, right? Well, if you look at that, you'll see that these 4 are small telescopes. They're 4 meter, 3.6 meter. Subaru is 8. This is 4 meter. But then there are all these larger telescopes down here. And why are these guys way at the top? And the reason is because they have wide field imagers. Blanco has the dark energy camera, DECAM, its main instrument. CFHC has MegaCam. Subaru has Hypers Prime Cam. And then Vista is a wide field infrared survey. At least it's up until last year or so. Now it's going to be foremost. And so that says a lot, right? It says that these smaller telescopes, 4 meter telescopes, out-punch their weight way to the top. So if you're going to want to lead and you're a 4 meter class telescope, this is the thing to do, right? And remember, we're going to be essentially a 4 meter class telescope in this new era. So even though there are these instruments that exist, I mentioned that there are some large capability gaps. One is they don't have UV blue coverage. And UV, I mean U-band, like 3,000 to 4,000 angstroms. Hypers Prime Cam just doesn't have it. And that's the 8 meter class telescope. They start at like 4,000 angstroms and it goes up. They just don't have the capability. Rubin has a U-band, but it's very poor. It's a very low throughput. And their surveys, they're only going to do it a certain amount, as you'll see. So it's not very much. It's a very low throughput, and it's a smaller telescope. They also don't have things like rapid response. Subaru doesn't do TOOs, rapid response. And again, it's the fact they got to put a thing on the telescope and et cetera. And the filter exchange is 30 minutes. It's just not designed for that. And Rubin, it's doing its survey, right? It's going to have a few TOOs, but not very many, and that's just for gravitational waves. Plus, they don't have the CMOS fast imaging. They don't have this multiplexing thing I was mentioning where you can get spectra after, et cetera. They just don't have these capabilities. And if you look at those two, here's a primary mirrors. There's Rubin, there's Subaru, and you can see, Rubin's essentially a 6.5 meter because of its area. Subaru's 8.2. Do they have U-band? Well, Rubin does, but it's not great, and Subaru does not. Can they get to 28 to 30th magnitude of U-band? No. And you'll see why that's important in a minute, okay? Do they do TLOs? No. And the rest, so on and so on. Like, do they focus on low surface brightness? Rubin, it's still kind of unclear. Subaru is not good for low surface brightness. Do they have CMOS? Do they have this minute later spectra? And can you even access them for your project? Say you want to target some point in the sky or some set of targets, objects, you're not going to use Rubin. It's doing its survey, right, for the next 10 years. And can you do Subaru? Maybe, you have some access to, but it's on a telescope very little. It has PFS, which is the prime focus spectrograph now that is dominating the time, which uses the same optics as HSC. So it's taking up all of its time. And so you'll have some capability. Plus, it's, believe it or not, starting to age. It's 14 years old, and in 3 or 4 years, it's going to start It's getting long in the tooth, we'll say, right? But it's still working. But if you put WFI on GTC, now you have all of these capabilities, and it's a much larger telescope, so it's much more sensitive. So this is the motivation for that context of why you would do this. Okay. Here are some of the capabilities in a nutshell. It can do wide field to 29 to the 30th, and it goes head to head with Roman, like I mentioned. And there's a table here of a bunch of magnitudes per hour that you can use to get a sense of how deep it goes per exposure time in different filters. Extremely deep U-band, which will be relevant as you'll see. And it has low surface brightness capability, at least capability. We're focusing very heavily on having good low surface brightness capability for the instrument. Good pixel resolution, fast readout, 10 seconds or so. And it also has a 10-second filter exchange, so it changes the filter during readout. And there's no loss in time on the sky, which is very different than Cypress Cam, which is 30 minutes, literally, to change the filter. And it's got, you can have update filters currently in the design, the usual 5 broadband, and then it'll be future narrowband and medium band filters, which is a capability that, like Rubin, for example, doesn't have. And this other stuff I just mentioned, rapid response capability, fast pipeline, data pipeline, et cetera. So when you look at those magnitudes, to help you make sense of that, if you're not that good with magnitudes, the Hyperspace Prime Cam Ultra Deep Survey goes to this depth at the bottom here. There's no U-band, but it has these depths. And as you can see, in like 2 hours, you can kind of do that with WFI. But if you compare it to Rubin, for example, Rubin sensitivities for 30-minute exposure are these. So that's a really short, time. But if you take the 10 years, the 10-year survey, and stack all of those images, so 10 years from now, you stack all those images, you will get this depth per filter. Clearly, you see the U-band isn't that deep, but it's much deeper than each individual exposure. However, with WFI on GTC, this is how long it would take to get those same depths. And as you can see, it's much faster. Now, it's not an all-sky survey, so that's a big difference. But if you have a targeted science, like I want to get this target or this area or this 10 degrees or something, you can do it very fast, very quickly, very efficiently, and as soon as this thing is built. Now, Rubin has the deep drilling fields, right? There's 4 or 5 pointings where they're going to go very deep. This is their 10-year depth. So after 10 years, you stack all those data, they'll go this deep. That's getting deeper. You're kind of approaching 28, or you are approaching 28 in the U-band, but not beyond. And with WFI, this is the depth that it would take to get there. So as you can see, this is something that's very tractable for just a night or a couple of nights observing, depending on filter, to get 10 years stacked DDF depths. Okay, so this is a facility instrument for discovery and science, and it's going to be able to do things that no other telescope will be able to do for decades, not even 30-meter telescopes. And if we look at the landscape right now, from now, well, we'll just start with now. We have these telescopes on the bottom here, or listed here, I've shown you, and these are different wavelengths like ASCAP and Meerkat, which are these Square Kilometre Array radio pathfinder telescopes. You have Euclid, LIGO's running IceCube for particles, et cetera. These are all telescopes that will benefit from wide field imager to locate sources, host galaxies, et cetera. And if you look at this table, or this list here, is basically current telescopes in different wavelength regimes. The ones in bold are have wide field capability, which is all of them, I guess, except JWST. And so most major facilities built in the last 2 decades have been wide field or all sky facilities. And that's kind of, there's a reason, because that's kind of where science is going, right? I mean, it's doing this kind of wide field, all sky work. And as mentioned, so if we look into the next couple of years, we start seeing these, many of these are literally billion-dollar facilities. Depending on wavelength, we got DSA 200 and the Square, 2000 and the Square Kilometre Array in radio. There's Simon's Observatory. The Roman Space Telescope is being launched soon, very soon. The Cherenkov Telescope Array is being built and going, but will be finished in several years. KMT3Net and LIGO India, particle and gravitational wave respectively, are being built. And then there's even the next generation, because remember, this is going to lead for a couple decades now. You got to start looking into what's going to happen. There might be LISA, DESIGO, which is the Japanese space gravitational wave telescope, a Cosmic Explorer, and Einstein telescope. All of those are for gravitational wave detection. And then, of course, these last facilities are not wide field. but they will greatly benefit from wide field imaging. They need the deep imaging for like lensed objects and for faint sources, et cetera, like the James Webb Space Telescope, which is up, the ELT, which is, as you can see in the corner here, lower corner, being built, GMT, TMT, and then eventually the Habitable Worlds Observatory or whatever it will be launched next. So all these are future things that are coming up that need this wide field imaging. And this shows the current and then the future telescopes. So on the left or on the right there are a list of all these future telescopes. They're all, again, wide field, except you look at optical, they're not. Everything that's coming up in optical is not wide field. There's the Chinese Space Telescope going to be launched, the ELT, or all the ELTs, LOT, which is a large telescope, 14.5 meter that's being built in China, and the Habitable Worlds Observatory. Those are all not wide field, and this is where WFI comes in. So now I'm going to talk a little bit about science, and I'll just very briefly, because there's a lot of science this thing will do, as you can see, and it ranges everything from working with space missions to early universe reionization, high redshift galaxy and supernova work, transients, CGM, IGM, emission over megaparsecs, lens targets, very fast things like FRB, fast radio burst counterparts, luminous fast blue optical transients, which have these bursts that are very fast, etc. Large scale structure, galaxy luminosity functions, globular cluster and ultra compact galaxy selection, well beyond what we can do now into new environments, stellar population work, low surface brightness work, has a whole bunch of science there, even solar system, interstellar objects, etc. So it goes all across the map, right? A lot of science. I can't talk about all that science, obviously. I'll say just a little bit about the first four here, and then you can ask me questions later, okay? So when it comes to space missions, I already showed you this, right? You got a wide field imager field of view, and the field of views of Euclid and Roman. Importantly, some of their main science is to do like weak lensing, for example, of the universe, and that requires photometric redshifts. You can't get spectroscopic redshifts of everything. But for photometric redshift, it's well known that you need U and G band to look for the Balmer break to get the photometric redshift. I mean, U band makes an enormous difference in photosees. Yet they go deeper than anything that's out there, so this is not going to be done unless you have something like the wide field imager. Also, Roman, for example, is focusing on redshifts 2 and 3 galaxies, Lyman Break galaxies. Those require a U-band dropout. They're dropout galaxies, if you know about these, and you need very, very deep U-band. Again, it doesn't exist. So it's crucial to have this to even get this science done for these telescopes, along with many other things that they'll do. This is the range, UV satellites are down there in the very blue. We've got Roman and others in the infrared, and WFI is in this range here. So it's filling this gap for this extreme depth. So this is 28, 29, 30th magnitude depths. Then there's reionization. So this is a nice, block, a cosmological simulation of a cube of the universe. It's all neutral. And then these little blue regions are where ionizing regions are forming around galaxies, right? Back in high redshift. Stars and supernovae produce ionizing radiation around galaxies, and they form these ionizing bubbles around them, as you can see forming in the blue there. And those bubbles grow and eventually connect. And at around redshift 6 or so, the universe became reionized. So we have an ionized universe. But what are those sources? And what caused that? How did that happen? And trying to map that out is tough. Now, the neutral gas, there are radio telescopes now that are being developed to map that at that redshift, mapping the neutral gas, but there's nothing to map the ionizing region. Now, this ionizing gas is Lyman continuum photons, and those are photons that are shortward of 912 angstrom, so you have high energy photons. So think about the ultraviolet, right? 912 angstroms and shortward is what's these photons that are being emitted or ionizing the universe. So at these redshifts, that's when you're looking at that, that's all redshift, so it moves into the optical. Okay, those wavelengths. And here's the spectrum of a redshift 4 galaxy. To this right part of it, all the way from 1200 to 1800, is the UV continuum from stars and like O and B stars. There's a really big emission line from Lyman alpha there at 1216. Then there's Lyman alpha forest, which is a continuum that keeps going on shortward, but there's a bunch of optically thick sources in line of sight which absorb that, so it brings that down a little bit. And then 912 is right here where this dotted line is. So anything short of that can ionize regions around that galaxy. Okay, so if you measure that there's photons coming out of that galaxy and getting out into the universe, you're saying that galaxy is ionizing its surrounding material medium. And so this is a 2D spectrum down at the bottom of this kind of this left part of it from like 740 to 1150 or so is now shown down at the bottom in 2D. And you kind of see the spectrum of the galaxy, which is this Lyman alpha forest. And that blue box shows you the Lyman alpha continuum, so basically from 912 shortwave. And there's a tiny bit of flux there if you squint your eyes, whatever, right? But there's a little bit of flux there. And it's hard. This is really, really faint stuff. This is like magnitude 28 and fainter flux. It's really hard to reach that. This particular galaxy is lensed a little bit, so we have the advantage of that. But to do this for galaxies in general, you need really, really sensitive telescopes and imagers. And so it's this region that we're searching for. And if you overlay what that redshifted flux hits in the optical, you have the U, G, R, I, and Z band here, right? So these are your filters. And you can see it lands smack dab in the U band. And so you need U band to do this. And U band only. The reason for that is, if you look at higher redshift galaxies, closer to redshift 6, that flux is going to now move into the G band, but the universe becomes opaque. It's more and more neutral. And about redshift 5, it's so neutral that you can't see that flux no matter how big your telescope is. So if you're ever going to do this, you have to do it from redshifts 3 to 5, find all the galaxies that are doing this, find other properties that they have that are associated with the Lyman continuum leaking, like does it have strong emission lines in the nebular lines, or does it have certain features in their outflows or whatever? You find that, which can be observed at high redshift, and then you look for galaxies at higher redshift and make that connection. So redshift 3 to 5 galaxies are analogs to redshift 6 and above, galaxies that are ionizing the universe. That's the only way you can do this work. And so study at 3 to 5 is as close as you can go, and you need U-band. Wide field U-band, because these are rare sources. That light has to make its way to Earth, and transparent sightlines to Earth are rare. And so you've got to have a wide field that goes crazy deep to do the science. Otherwise, it just doesn't get done. And if you do it, you can map the universe in ionizing radiation. I'll also mention high redshift supernovae, and by high redshift, I mean greater than 2. This has been done for some decade and a half now. Our team has found a whole bunch of them. In HST surveys and JWST, they're starting to find them, usually lens, but they'll find some of these. So at high redshift, same redshifts as I'm talking, redshifts 3, 4, 5, etc., you find supernovae. And Rubin will uncover a bunch between 2 and 3, and Roman will find a whole bunch out to 12. And if you have deep surveys, which you can do with Roman, you can actually find them to 20, and JWST can actually find those out to redshift 20, which is kind of the first stars. And I'll just skip to this, but I can tell you a bit about why you would care about high redshift supernova, but they created the elements and, energies and densities that are really very high. You can do things like measure the expansion rate of the universe, right? Dark energy, map dark energy, chemical evolution and star formation rate of the universe, their impact on reionization, et cetera, et cetera. But they do also impact galaxy formation because they create these outflows and these chimneys and stuff in galaxies to interact with their CGM, et cetera. Anyway, there's many reasons, high utility for these things, but this is back to where I was showing you. So there's a lot of these supernovae have been found, but we're gonna get thousands more once Roman launches and Rubin gets going. Thousands, okay? So that's good, but there's a big problem. And the problem is we don't know what they are. Okay, so the problem is all supernovae are classified by their rest frame optical. That's historical. That's what's been done because they've been found locally to us. You look at the rest frame optical light curve or the rest frame optical spectra, and you say, oh, that's a type 1A or that's a type 2P or whatever, right? But if you look at their UV, no clue. You can hand UV light curves or spectra to an expert, and they're like, yeah, I don't know, it might be this. Unknown, just complete, very little known about the rest frame ultraviolet. However, at these high redshifts, that's all you're seeing. You're looking at their rest frame ultraviolet. You see their rest frame ultraviolet light curves, you see their spectra, and their rest frame optical, once you get to redshift 4, is redshifted out of the near IR, so you can't even get it with that. So you're stuck here looking at a bunch of rest frame UV spectra, and you have no idea what you're looking at. How are you going to do science with this, right? And there's thousands coming. And so what we need to do is understand, we need to make a UV classification system for supernovae. And how would you do that? Well, the solution is to use something like WFI on GTC, because now you can hit several square degree patches, image about once a month, maybe even 2 months, because these things evolve very slowly. And the reason I say that is because supernovae take maybe a month or two to evolve. Superluminous supernovae take hundreds of days to evolve. But now you have time dilation, because at high redshift, you 1+ said time dilation. So now you've got things that are evolving over a year, 2 or 3 years, and you can sample that every month or so, and you got a good light curve. And so if you just get a couple, several square degrees of deep imaging, you can find these things in their rest frame UV, map their light curves from start to finish. And then if you do it between redshifts 2 and 4 as an initial sample, you can get their spectra with GTC and other things like JWST. You get the rest frame UV spectra, maybe even with ELT at some point too. And you get the rest frame optical spectra with JWST, and you say, now I can connect their optical with their UV, and I can make it develop a system. So you get a whole bunch of rest frame optical high redshift and a whole bunch of rest frame UV, and you're connecting those together. Why wouldn't you do this at low redshift, which sounds logical? Is because it's really hard, believe it or not. You have low volumes at low redshift. You have only HST to do the UV, and HST is not long for this world. But we're trying to do that already with programs, and we have a big program that is going to get 6. I mean, 6 isn't great, okay? And it's hard to get spectra, but non-intuitively, it's easier at redshift 2. They're all over the place. You got big volumes, and you can use JWST to do it. So it's kind of weird, but it's true. The best way to go about this is at redshifts 2 to 4. So yeah. So, and the U-band is essential because at redshifts 2 to 4, we're back again to looking for galaxies that have dropouts. Their UV's dropped out, or the supernova has a dropout from the Lyman continuum. And so this is, I can go into this if anyone cares, but this is a very successful method where you image very deeply. Say you do 4 square degrees with WFI. Each year you're just mapping that and you're monitoring that. You then look at each image and say, I've found all the galaxies at redshift, say 2 or 3 or 4 by using Lyman break galaxy selection techniques or some efficient galaxy selection technique. And you see the galaxies, you just monitor them every time to see if anything changes. And you start seeing supernovae show up in these things, even if you stack yearly amounts. I can get into details about that, but it's a very easy way to just identify high redshift galaxies, the redshifts you want, and monitor them over time to find supernovae. You find all those supernovae, you go after them for spectrum. And that way it's like 95% efficient. You don't have to worry about it being low redshift or some AGN or something else that you're not wanting. And this works out really well. Okay, so that's that. So you need WFI for that. So the high redshift you're seeing by WFI is you want to look for Lyman continuum galaxies in this redshift range here, understand them, understand properties that are associated with those that are leaking Lyman continuum flux, and then connect those two galaxies all the way back in the universe. The SKA and other radio are going to map this in neutral hydrogen. So you would have ionized maps and neutral hydrogen maps. So you can map the universe over time, which would be fantastic. You can find those stars here that I mentioned, supernovae that are dying at redshifts 2 to 4, and understand their properties to then understand all of those that are found all the way up to redshift 20. So this is the thought. Okay, so I'll just talk about transients for just a couple minutes, other transients. When it comes to just all kinds of transients, which are beyond supernovae, but include supernovae, there used to be a few or hundreds, now there's thousands, and there's gonna be millions, right? I mean, it's just crazily growing. And there's things from gamma ray bursts, which are the most extreme explosions, which still need localization from many facilities like Fermi, et cetera. So you need a wide field imager to find them in their host galaxies. Supernovae, which I just talked about, you get their UV outbursts. You can understand type 1a progenitors by seeing UV bursts of if they eject to hit their companion stars, et cetera. Tidal disruption events, you can study those from low redshift to high redshift. There are gravitational waves, right? Compact sources merging together to create kilonovae. And those also have poor localization, so they need wide field imagers to follow it up, especially out to decent redshifts. There are things called LF bots, luminous classical optical transients. These things explode with the luminosity of a extremely bright supernova, so -20, all within a couple days, fades really fast. You say, okay, that's great, but fantastic energy. Then they explode again and again and again, and one has been seen to explode 14 times with similar energies and over 10, 20 minutes per explosion. What the heck causes that? That's weird. We want to find that out. Okay, so these are crazy. Flaring stars, of course, these are things that are everywhere, but also characterizing them to good depths all the way in our galaxy, help to understand habitability, whatever, the ability to habit planets around them. There are fast radio bursts and all kinds of ultra long period radio bursts that we need to understand. Do they have counterparts? A lot of theories say they would have an optical counterpart to some depth, but that depth is much deeper than what we can do currently. So maybe those CMOS detectors on WFI could do that. There's even high energy particles that come raining in, and we want to try to find out the sources of those, like are they from AGN or other cosmic things. That's the FRB counterparts I mentioned, and this is the LF bot things where they explode very fast. If you wanted to see a plot of that. Okay, so this is just one of the many explosions in the AV magnitude. Well, oh, it doesn't have the absolute magnitude, but anyway, that works out to, yeah, anyway, that works out to about -20. Kilinovae, I'll just say really quick, from here forward, the only thing large to follow up kilinovae, because they have been difficult, as we all know, they're hard to follow up. 1 meter and 2 meter class telescopes can find them in the local universe, as you'll see. To find them out farther and beyond what the gravitational wave detectors can detect, all we have is the dark energy camera. And Ruben will also go after some of them. So that's these 2 telescopes down here in the south, and they get this region here. A WFI would be in the north here, so it would cover all of the north and the overlapping region here. So that would provide, at least in the future, something else, right, to get gravitational wave detections. And it will get about a 10-fold increase. So this is just a volume plot to show you that 1 meter class telescopes can reach around us in that blue region, and 4 meter cam can reach to the green. And then, of course, WFI would reach this very big region, which can go out to almost redshift 1 beyond gravitational wave detectors. So you can actually maybe even see evolution. You can find these things firstly, but you might be able to see redshift evolution. And you can do blind searches without gravitational waves, and there's a zillion reasons why you'd want to do that, just to look for kilinovae from their optical signatures. All right, that's a lot of science, so I'll stop there on science. Just to end up here, I think I'm about there. Here's a bunch of the capability gaps. So it has extremely deep U-band for this wide field imager. HSC has no U-band, Ruben has poor. It has extreme depths overall for all different filters, so that's good for these space missions, as I mentioned. Fast readout with these CCDs, also with CMOS, to do these fast science things that HSC and Ruben do not have. Fast filter change, which HSC does not have, and is narrowband capability, which Ruben doesn't have. This rapid response capability I mentioned, neither of them have, so I think that's going to be fantastic. Low surface brightness design, I think, is going to be very important for the future, as people here know. And I think that's going to really change things because HSC is not good for that. And then there's this fast multiplexing spectroscopy. So what's been done is we've been working on the design a lot, and we have designed the detector, and one version of it over there with Australian and Caltech engineers, kind of a model of the whole thing there. And there's the barrel over here, which is holds the lenses. And there's actually been fabrication of that barrel with carbon composites for lightweight, strength, et cetera. There's the optical design I mentioned to you. Here's the filter exchanger. It's actually the deck. Anyone here use the dark energy camera, deck cam on Chile? Anyway, if you have, it's fantastic. It's really easy to use. But the filters are, 600 millimeter, gigantic, but it moves them in and out in about 10 seconds, 8 seconds. So fantastic. And we got the design from them. They said, yes, you can use this. So we just took the design and modified it for this. Those are the giant filters. And so there's the filter exchanger, which we've actually built one of those layers. And I guess that doesn't work. Maybe it does. And that's about how fast it would be to change a filter. So say you have a filter in there right now, which is now with that hole, and then you say, I want to change filters. You could start your stopwatch, and it's about 10 seconds or so by the time the next filter gets in there. And so it's a fast exchanger. I mean, that's an old footage, but we tested it many times. And we're also developing pipelines and et cetera. So this is the summary, technical summary. very high throughput. It has the atmospheric dispersion correction, which I can talk to people about, which is active. Has these quantizing CCDs, which have like zero noise, which is crazy. Okay. So it can go really deep. It's got industry 4.0 technology with digital twin and smart sensors. So it's a smart instrument, et cetera. It uses heritage things like dark energy camera. The detector's kind of this Zwicky transient factory design. So there's heritage there, and it's got a great team. So this is the last slide, summary slide. Those are kind of the bullet points of what I've said 1,000 times. This is a possible timeline at the bottom. I mean, we're up to 2026. So we're working in a major funding area. And then once funding arrives for the build, then we can have first flight around 2030. Thank you.
Okay, so thank you for your talk. We start with the questions. Is there anyone who wants to? Yeah.
Plenty of questions. So, for example, what about the pixel scale? Because I mean, is any reason why you are sampling the field of view with multiple CCDs instead of one very large CMOS, for example? Can I have the microphone for one?
Pixel scale is. So the question is, what is the pixel scale? Because we have CCDs, right? And then did you say something about CMOS or no? Hmm.
Now we have CMOS that are able to cover, I mean, that field of view pixel scale of maybe 0.3 arcsec or so. So what is the pixel scale you have?
Okay, so the pixel scale for the CCDs right now is 0.145 arc seconds per pixel. That's the design. Depends on the seeing and sampling, but we don't necessarily need that small, but we're planning for like the best possible seeing to make minimal impact, right? To be able to, because the instrument makes minimal impact that sample it well, but it can be larger. The CMOS are in the corner right now for like guiding and focus and things like that, but can be used for science. And so those aren't like mapped one-to-one with the image. You can just target an object in those corners if you want to do that in the current design. But if we do get CMOS across the whole thing, if it has sufficient UV sensitivity, which has been the trick, then it would be a different pixel scale across the whole thing. And those are usually 10 micron pixels, so it's going to be even smaller, but we would have to work on how to sample that because the current pixels are 15 micron pixels, so you'd have even smaller sampling with that. Does that help? Yeah.
But I mean, the second question. You can.
Yeah. Perfect.
Okay, great.
Okay.
Moving the secondary mirror, it's great, but I mean, you need to probably be sure that the precision is perfect, right? Because otherwise, the full optics goes crazy. So, is that an issue, or do you think you have that precision to put back the secondary mirror to the right location?
Okay, so firstly, the deployable secondary is an option that may or may not happen because you can still just install the instrument or not, right? But if you do that, currently the design shows a very good reliability. But I think at this point, to ensure that, you would bring it in, do a mirror line with the secondary, which takes 10 or 15 minutes, no, 5 or 10 minutes. I don't know how long, approximately, right? When you take the mirrors, the primary, and you phase it with the secondary to tilt the secondary. So you would probably flip it in, do a check, and then start observing. Does that help answer that? Yeah, because you can do a phase check right there. Yeah, but that's an optional capability, right? Yeah, but it currently shows it to be sufficiently reliable. But you want to test it now because reality is a different thing, right? Exactly. Yes.
Hello. Thanks
Hi.
for the very nice detailed talk. I wanted to ask, since as you said, we do not really know how the transients, because I'm more interested in the transients, would look like in this part of the spectrum. How much would you expect the framework that we have now to change for higher redshift transients?
So for supernovae or for others?
In general.
In general. So first for supernovae, I think there are a few things like type 2N, not much different. Superluminous supernovae, there are three UV spectra, which not a lot, but if they all look the same, which, I don't know if they all look the same, not too much as well. But for all of the other supernovae, there's going to be a lot, because when you start seeing the different types, 2B, 1B, 1C, and all these, and then variations on those types, a lot changes in the UV. And so you're going to have a pretty big sample of a lot of the core collapse supernovae to do that properly. So some of them, not too much difficulty. Superluminous, not much, I don't think. And those are the ones you can see the highest redshift, which is, yay, that's great. We can do that work right away. Type 2Ns, you also are very UV luminous. You can see those far too. That's going to be easy. But when you get all the other ones, 2Ps and stuff, it starts becoming tough. Now, when it comes to other things like LF bots or, I don't know, some of it, who knows? It's wide open, right? You just need to have something to understand what they look like. Yeah, because there's nothing. So, yeah.
Thank you.
Yep.
Very, very, very nice proposal.
I think.
I hope it'll be a reality sometime.
Okay.
I have also many questions, some of them during the coffee break. Coffee. You mentioned space. I mean, I suppose this is another talk, but are you working on a space version of this?
Oh, no, this is for ground, just for 10-meter class telescope. So GTC is what this is for. This is not, we don't have a design for space. And there's nothing, I mean, for NASA to build something that's going to be a wide field imager that can get these depths, there's nothing on the drawing board. Only thing they have right now that's next is this HWO, which is the typical, 3 arc minute or something. So you're just, yeah.
What about ultrasat? You mentioned it, but you haven't said much. How does it compare with ultrasat?
Ultrasat is only in the UV though, so it's like 2800 angstroms in shortward. So that is, complementary. It also has, well, which one is it? Ultrasat or UVEX? Anyway, I think ultrasat's pixels are still pretty big, so that makes it less. You get better higher resolution with this, etc. Yeah. So similar, whatever, but you got your separate wavelength ranges. Yeah.
Another thing is that we haven't mentioned, at GTC we have already a hypercam.
Yes.
That is very popular.
Yes.
And you get all the filters simultaneously. How will this complement hypercam?
So it's firstly the wide field, which is what I think is going to make a difference. If you're going to do any kind of like survey or search for something that's a transient over some big area, you need wide field. You can't map that area with something small. It just takes too long, and they change, and they transients fade, and you miss them. So the wide field's number one. The height, the optics are so efficient. They're like 95 to 98% all the way through, and it's a single reflection. It's just really efficient. So it's going to go deeper, which I think will matter. But when it comes to like the CMOS, it's not probably much different than what your capability. Yeah. Other than it has that sensitivity and blue. Yeah.
And my last question. Any possibility to add some spectroscopic capability?
Have some
Spectroscopic capability.
Yeah. Well, we played with, what is it? A grating, to have a slitless spectroscopy. That's, I don't know. It's pretty tough, and it gets complicated. Yeah, and it'd be really low resolution. So yeah.
Okay, thanks a lot.
Yep.
So 2 more questions. So here, regarding what he was saying, so the hypercam is tiny. Some people have been talking about increasing a little bit the area and so forth, sacrificing a little bit the pixel scale, which is tiny as well. So in instruments like this, the possibility of having multiple bands simultaneously is no way, because it complicates your life, or decrease the sensitivity. Or, because that would be really impressive if you can make it the 5 filters at the same time, for example.
Yeah, you mean like 5 detectors, like
Exactly. So like hypercam, but in this large field of view.
Yeah, well, I would say that I would love that, and that would be wonderful, but that's a lot of money, because you can imagine detectors.
Is it a matter of money simply, or it's simply also you decrease also the throughput?
It's a matter of money, but also possibly space, because in the prime focus cage, if you've got all of those cryostats, you can start getting big and heavy and complicated, maybe. But yeah, it might just be money. But now you can do split filter where you're doing part of the, field of view with different filters and rotate, but it's not simultaneous. That's more, that's no, yeah.
And what about the cost? Or did you say anything? How much?
Oh yeah, so the cost of this, that's a good point. The cost is about, it's estimated to be with contingency 18.9 million US. So for wide field imagers, that's very expensive because they're usually 30 or 50 or something. But mainly because we're using a lot of technology that already exists. And so we've made it low cost. But say 20 million US is the approximate cost, yeah. Mm-hmm.
Any more questions in the room? No? I think we don't have any in the chat.
I'm good.
Okay, so I guess we're finished then. So
Okay.
thank you. Thanks a lot
Yeah, sure thing.
for the
Thanks.
the
Thank you.
questions and everything.